I welcome you all to the session of engine system and performance, and today we shall discuss about performance map of superchargers, and then we shall solve one numerical problem to illustrate the performance of superchargers following the technical discussion we had in our previous class. So, we have discussed about performance map of SI engines, and if you can recall, this particular map is very useful to compare the performance of two dissimilar SI engines, and we have discussed this part in one of our previous classes. And today in the context of superchargers, we shall see why this map is important, and in this map what are the information depicted from experimental observations or measurements, and we shall see whether this performance map really can provide us qualitative or quantitative estimate about the design parameter or compressor. So, if we try to recall, in our previous class we have discussed about superchargers, and we had seen supercharging the internal combustion engines or high speed internal combustion engines is very important, essentially from the perspective of better efficiency. And we had seen that supercharging is one of the feasible avenues by which it is possible to increase the air consumption rate to be inducted into the cylinder during intake stroke. What we had discussed is that the density of intake air should be increased, essentially to increase mass of air for a given displacement volume of the cylinder as well as given speed. If we increase the speed, certainly we can have larger or greater amount of mass of air to be inducted, but increasing the engine speed increases frictional losses as well. So, let us discuss about what is this particular map in the context of superchargers. So, if we try to recall, that supercharging is nothing but increasing the pressure of intake air using a mechanical device, that is compressor. So, when you are talking about performance map of superchargers, it is nothing but the performance map of a compressor or rather compressors. So, if we try to draw the block diagram, and let us first discuss about this. So, supercharging if we discuss the supercharging, that is to increase the density of intake air. That is, we have discussed, rather that is what we have discussed in the previous class, and this is done by increasing the pressure of the intake air by a compressor. If you can recall, in the previous class we have discussed that to run the compressor, again we need some energy to be supplied to the compressor. Now, this turbine this compressor can be run or can be operated using mechanical system or mechanical device, that is called mechanical driven, mechanically driven compressor. So, we need one compressor to increase the pressure of the intake air, and to run the compressor again we need to supply certain or some amount of energy in the form of work, and that energy should be borrowed from the engine itself. And there may be a case that can we use the exhaust gases of the engine itself to run the compressor through a small turbine, and that is called turbocharged. So, it can be mechanically charged or mechanically assisted or mechanically driven compressor, or we can have turbocharged system. So, if we try to draw the block diagram, so let us draw if this is the engine block, and exhaust gas is taken to run a turbine, right. From there exhaust gas or exhaust gases come out from the turbine, exhaust gas. Now, if we can have one small compressor connected to the shaft of this turbine, so that that we can have this compressor. So, this is C, and this compressor is taking air from the ambience, and that air which is compressed is now fed to this engine cylinder, right. So, this is the block diagram of supercharging unit, but essentially from the schematic depiction you can understand this is turbocharged. So, if it is, this is the engine, this is turbine T, and then this is compressor. So, the idea is to use exhaust gases, exhaust gases. So, the exhaust gases are used to run this turbine, small turbine, and the compressor is connected to the shaft of this turbine. So, as the turbine is rotating, this turbine is acting to drive the compressor, rather the power output from the turbine is used to run the compressor, and compressor is used to compress the air, and that compressed air is supplied to the engine. So, this entire unit is known as turbocharged. Sometimes that I should mention here that here one particular device is used, and that is known as aftercooler. Okay. So, this is the turbocharged. Essentially we are talking about performance map of the superchargers, means performance map of the compressor itself, because we need to know about this particular device. That means we need to supply certain amount of energy to run this unit, that is this compressor. At the cost of that input energy, what is the rise in pressure of the intake air, and that is important to know. So, if we look at this map, and this map is essentially the performance map of the superchargers. As I told you before, performance map of superchargers is nothing but the performance map of compressors. So, what you can see from this performance map, essentially idea is to obtain pressure ratio that you can see along y axis. We need to know the performance ratio, sorry, the pressure ratio. So, we need to know the pressure ratio, that is P pressure ratio Rp, that is P exit by P inlet. So, exit pressure of air to the inlet pressure of air. So, as the air passes through the compressor, there is a rise in pressure. So, the air pressure at the exit of the compressor to the pressure of air at the inlet to the compressor, this is known as pressure ratio or RP. So, what we are trying to have in this map to obtain pressure ratio for different values of mass flow rates. So, that means if we keep on increasing mass flow rate of intake air, then what would be the value of pressure ratio for different speeds of the compressor, and if we can collate all the data, and if we can represent all this data, and that map is which will be obtained is known as performance map. So, if we look at this performance map carefully, we can see that in this map there is a maximum efficiency line. So, if we mark this, so this is the maximum efficiency line that we can see. There are iso-efficiency lines that we can see, and those iso-efficiency lines are presented using green colored line, and in addition to these two different lines, that is maximum efficiency line and iso-efficiency lines, in this map iso speed line, what we can see, in addition to iso-efficiency lines, maximum efficiency line and iso speed lines, these two lines are also predicted or depicted in this map. Most importantly, if we look at, we can see there is a particular boundary which is a line denoted by dotted red colored line, which is known as surge line. We shall discuss about this particular line in this context. Also, we can see choke line, which is shown here using blue colored dotted line. So, these two lines are very important to know before we go to solve a particular numerical problem. Now, as I said you, let me explain once again what is done. The entire objective is to obtain pressure ratio with change in mass flow rate, and if we do this at a given speed, we will get one particular line. If we perform this task for different speeds, then we will get this map, that is performance map. So, that means the first objective is to get pressure ratio experimentally, of course, or rise in pressure of air as it passes through the compressor for different values of mass flow rate at a constant speed. If we do these experiments, or if we perform this task for different speeds, then this map can be obtained. In this map, in addition to this iso-efficiency line, there are two different lines as well, we can see from this map. One is maximum efficiency line and another lines are iso speed lines. Okay. What we can see, towards extreme left of this map, there is an important line denoted by red colored dot line, and this line is known as surge line. So, this is essentially a check mark or check line, because a designer or operator should not allow the compressor to run beyond this line. So, that means this is the check line, while this line which is known as choke line, shown here using blue colored dotted line, is also very important to know. As such, these two different lines are the border lines of compressor operation. So, the operator should run compressor between these two lines, any point between these two lines, at any point between these two lines. Now, let us talk about the significance of these two lines, that is surge line and choke line. Surge line is very important because surging is really an undesirable phenomenon in the context of compressor operation. So, it is nothing but oscillation, that is, as the air is allowed to pass through the compressor, it oscillates between inlet to exit of the compressor, and this phenomenon is associated with flow reversal as well. So, this is not desirable at all. So, surge line is obtained. So, we need to know a particular mass flow rate for given speed, for which we will obtain this surge line. So, let me tell you once again, this is very undesirable phenomenon of compressor operation. The problematic issue is air mass which is entering into the compressor starts oscillating, and it oscillates between inlet to exit of the compressor, and it is also associated with the flow reversal. So, this line, if we take any point, then compressor will not be able to run stable, so it would be unstable operation. So, if we go further leftwards from this line, then it is highly unstable zone. Stable zone is rightward of this particular line, that is surge line. Now, let us come to this particular line, that is choke line. So, choke line is essentially a line which is also demarcating compressor operation from non-operation zone to smooth operation zone. What is this line? We have studied about choking in the context of nozzle. So, we have studied that in a convergent divergent nozzle, if we decrease the pressure at the exit, that information should reach at the inlet of the nozzle to increase the mass flow rate, because flow rate is dependent on the pressure drop. So, if we create even further drop in pressure at the exit of the nozzle, that information will not be sensed by the nozzle inlet to increase the mass flow rate, because that is called sonic state will be achieved. So, a further decrease in, so there is a threshold value of pressure ratio or exit pressure, and if we reduce exit pressure beyond that threshold value, there will be no change in mass flow rate through the nozzle, and the nozzle is said to be choked. Similarly, here also it is, if we increase the mass flow rate, the rise in pressure ratio will not be there, rather the pressure ratio drops. So, what we can see, this particular line is representative of those points where a further rise in mass flow rate will not allow the rise in pressure of that air mass, and if we can take the locus of all these points, then we will get this line, that is choke line. So, that means if we allow the compressor to handle larger amount of air mass, but the rise in pressure will not be there, rather pressure rise drops. So, there is a sudden drop in pressure rise with increasing mass flow rate of air, and with increasing mass flow rate of air, the compressor speed will increase, frictional losses will increase, but the eventual gain will not be there, because we can see from this, if we traverse from this if we traverse along this line, we can see though the mass flow rate increases, but the pressure rise is not that. So, pressure drop, pressure rise drops. So, this is again very important line to be taken into account for the compressor operation. So, what we can see from this performance map, this map gives us a qualitative information about the compressor operation zone. So, the operator should be knowing that compressor can be operated anywhere between these two lines, that is surge line and choke line. So, this map is very important to give us, again I am telling, some qualitative information about the safe operation or safety operation of the compressor. So, with this, now let us move to solve one numerical problem to illustrate the theoretical part that we have discussed in the previous class in the context of supercharging. So, if we go to the problem statement, let me read the problem statement first, then we shall solve this. An 8 cylinder 4 stroke cycle diesel engine operates at 2400 rpm. It is provided with a turbocharger, though we have not discussed anything about turbocharger until today, but we had discussed today the turbocharged unit. So, we shall draw again this particular unit schematically before solving this problem. It is provided with a turbocharger and an aftercooler. The bore and stroke length of the engine are 125 millimeter and 155 millimeter respectively. The volumetric efficiency based on inlet manifold condition of 1.8 atm pressure and 325 Kelvin temperature after the aftercooler is 0.85. So, volumetric efficiency that is calculated based on the manifold air condition or manifold conditions, those are basically pressure and temperature, that is 1.8 atmospheric pressure and 325 Kelvin temperature after the aftercooler is given at 85%. The compressor and turbine isentropic efficiencies are 75% and 60% respectively, that is 0.75 and 0.6 respectively. The ambient conditions are 1 atmospheric pressure and 300 Kelvin temperature. Calculate the following: the power required to drive the compressor of the turbocharger. If the exhaust gas temperature from the engine is 950 Kelvin, calculate the pressure at the turbine inlet. So, this is very important. Assume that the turbine exhaust to the atmosphere. So many data are given in this problem statement. As such, we can have many information from this problem statement. So, what we can do, first of all, let me schematically draw the turbocharging unit, rather supercharging or supercharger, which is equipped with our supercharger and turbocharging. So, basically that compressor will be operated using a small turbine and the turbine will be driven by the exhaust gases of the engine, that is what is important. So, let me solve this problem statement, this problem. If we draw the schematic, we will have one turbine and this turbine is operated or driven by the exhaust gases, and this exhaust gases are coming from the engine. Then it is given that turbine exhaust to the atmosphere. So, this is turbine exhaust. The turbine is connected, the small turbine is now will operate the compressor. So, typically I should correctly draw. Typically turbine and compressors are schematically shown like this. In the turbine gases expand, while in the compressor gases are compressed. So, this is compressor inlet, intake air from the atmosphere, and then compressor compresses the air, that air is taken to the after cooler and finally taken to this engine. Okay. So, this is the block diagram, this is compressor and this is the common shaft and this is after cooler. This after cooler is provided, if you can recall the discussion we had in our last class, when compressor is compressing the intake air, temperature also will increase. If temperature increases, the rise in temperature will be increased subsequently in the engine itself, right, because this air will be taken during intake stroke to the engine. So, this is engine, and if the temperature is if the temperature of intake air is higher before it enters into the engine, subsequently its temperature will rise further and it will create some operational issues for the SI engines, because it will create knock or detonation. So, that is not a desirable phenomenon at all. This phenomenon is not a desirable phenomenon at all. So, what is done is this particular unit, that is after cooler, is incorporated here to reduce the temperature of intake air before it enters to the engine. Okay. So, this is the schematic depiction and this entire unit is known as turbocharge or turbocharger. So, this is turbocharged compressor. Let me tell you one thing, the compressor can be mechanically charged or mechanically driven, but in this case the compressor is driven by this turbine, small turbine, and this is known as turbocharged compressor. So, let me write turbocharge compressor. So, if we go to solve the problem, what we need to first calculate is the stroke volume. Stroke volume Vs equal to pi by 4 into bore diameter square into bore length. So, it is given bore and stroke length. So, bore diameter is 125 millimeter and length is 150 millimeter. So, if we use this value, that is 0.125 whole square into 0.15 meter cube. So, this is coming as 1.83 into 10 power minus 3 meter cube. So, that is the stroke volume. Now, if we can calculate inlet air density based on the manifold condition. Let me go back to this statement once again. It is given the volumetric efficiency based on the inlet manifold conditions of 1 are basically of 1 so conditions are 1.8 atmospheric pressure, 325 Kelvin temperature and the volumetric efficiency is 0.85. So, what we can do, that we can calculate density of inlet air based on the manifold conditions, those are 1.8 atmospheric pressure and 325 Kelvin temperature. So, this rho inlet equal to P inlet divided by R T inlet. So, it is given 1.8 atmospheric pressure. So, 1.8 into 10 to the power 5, if we go for unit conversion, the value of R is 287 and T in is 330. Okay. So, this if we calculate it is coming as 1.9 kg per meter cube. Okay. So, this is the density of the inlet air based on the manifold conditions. Okay. Now, having calculated density of inlet air based on manifold conditions and knowing the volumetric stroke volume or displacement volume, we can calculate the amount of mass to be inducted theoretically to the cylinder or to the engine. So, let me write here theoretically mass flow rate of air, theoretical mass flow rate of air per cylinder per cycle, it would be how much? Stroke volume or displacement volume, that is 1.83 into 10 power minus 3 kg per meter cube into rho in, that is kg per meter cube. So, that is kg. So, into 1.9 kg. So, this is coming as 0.003477 kg. So, this is the theoretically calculated mass of air to be drawn into the engine cylinder per cycle. Okay. So, now let us calculate, this is not the mass flow rate of air because this is mass of air. So, I should write this is not the mass flow rate. So, this is mass of air. Okay. So, this is theoretical mass of air. Now, if you would like to calculate mass flow rate, then we need to know the RPM. So, if we go to the next slide, having calculated theoretical mass of air, now we can calculate actual mass of air per cylinder per cycle, that equal to because we know volumetric efficiency. So, we know this volumetric efficiency equal to actual mass of air. This is defined as the ratio of actual mass of air or mass flow rate of air to be drawn into the cylinder to the theoretically calculated mass of air. So, if we remove now this mass flow rate, so this is the volumetric efficiency. So, this is theoretically calculated. So, this is theoretical. So, from there we can calculate that this is, so m dot or m actual equal to eta volumetric into m theoretical. We have calculated eta volume is 85%, that is given in the problem statement, and theoretically calculated mass of air is 0.003477. So, this is kg and it is coming as 2 point. So, this is coming as 2.95 into 10 power minus 3 kg. So, this is the actual mass of air per cylinder per cycle. So, per cylinder per cycle, that is very important. If we know in the problem statement it is given there are 8 cylinders. So, if we go to the next slide, so 8 cylinder 4 stroke cycle engine. Okay. So, 8 cylinder 4 stroke cycle engine, and then we can calculate the actual mass of air per cycle, that is per cylinder per cycle, that you have calculated this is the figure, that is 2.95 into 10 power minus 3. So, this is 8 into 2.95 into 10 power minus 3 kg, and it is coming as 0.0236 kg. So, this is again mass of or actual mass of air per cycle. Now, number of cycles per second, number of cycles per second, we know the RPM, that is 2400. 4 stroke cycle engine means there are 2 revolution in one cycle. So, this is revolution per minute, that is RPS, into there are 2 revolution. So, this is coming as 12. Okay. So, then we can calculate from this actual mass flow rate. So, we have written here mass of air, but now we are writing mass flow rate of air. Through the engine per cycle, right. It is not per cycle, rather per second. So, we can write here in terms of unit. So, this is 20. So, this should be 20, not 12 rather, because this is 20. So, this is 20. So, this is 20 into 0.0236. So, if I erase this part again, so this is 0.0236 and it is coming as 0.472, this is kg per second. So, this is 1 per second. Okay. So, we get it actual mass flow rate of air. Now, let us draw HS diagram, because if we look at the unit, if we can recall the unit, we can see there are 2 devices. First of all, the turbine is there, and then compressor is there. So, this is the compression of air, and then we have turbine. So, these 2 are connected to this common shaft, right. So, this is the exhaust gas, this is exhaust, and this is compressor, air in, air out. So, this is compressor, this is turbine. So, this is exhaust gas in, exhaust gas is out. So, what we can see here, air is compressed in the compressor while the exhaust gases expand in the turbine. So, if we draw the HS diagram, here, so what we can see, the actual compression process along with isentropic one. So, if we try to draw the HS diagram just for the sake of completeness. So, if it is S, so we know that this is H and this is the isentropic 1 to 2 to S. So, if this is P2, if this is P1, certainly P2 is greater than P1, then the actual process would be 2. So, this is the compression process. Okay. Similarly, if we try to draw the HS diagram for the turbine, so this is for the compressor, this is for the turbine, and we can define this isentropic efficiency of the compressor is, we know that actual work needed to compress the air should be much higher than the isentropic one. So, it is H2 minus H1, while this is H2S minus H1. If we assume that the specific heat of air is remaining constant, then we can write this is T2S minus T1 by T2 minus T1, while Cp air is remaining constant. So, you can write like this, this is T2S minus T1 divided by T2 minus T1, assuming Cp constant, okay, assuming Cp of air constant. Okay. So, for the turbine, if we draw the again these processes, then what we can see, this is P1 prime, this is P2 prime. Certainly, you can understand that P1 prime is greater than P2 prime. So, this is the isentropic expansion from 1 prime to 2 prime S, while the actual expansion will be like this. So, this is 2 prime. Okay. So, similarly, you can define here eta turbine. You can understand that if we use isentropic expansion of the gas, then the amount of work that we will get will be higher as compared to the frictionless or real compression, real expansion process. So, that is, it is essentially H1 prime minus H2 prime divided by H1 prime minus H2S prime. So, again if we consider that Cp of, because turbine handles exhaust gases. So, if we assume Cp of exhaust gas is constant, then we can also write this is equal to T1 prime minus T2 prime divided by T1 minus T2S prime, T1 prime minus T2S prime. So, these two are very important because we will be using these two expressions to solve the problem further. So, as I told you that for a constant Cp of air, we can write compression efficiency that equal to T2S minus T1 divided by T2 minus T1. So, from there we can calculate T2, that is exit temperature of air at the exit of the compressor, and that would be equal to T2S minus T1 divided by eta C. So, that is isentropic efficiency. So, this is isentropic efficiency, this is S efficiency plus, so this is plus T1, and if we plug in the value, what is T2S, because that we have to calculate in the problem statement. In the problem statement, it is given that P1 equal to 1 atmospheric pressure, right. The power required to drive the compressor. Now, ambient conditions. So, these are ambient conditions, T1 equal to 300 Kelvin, P2 equal to 1.8 atmospheric pressure, that is manifold pressure, and T2 equal to so 330 Kelvin. Okay. So, these are given. So, these are the manifold conditions, and these are the ambient conditions. Okay. So, if we plug in the value of here we get, so this is, and so then we can have T2s by T 1 equal to P2 by P1 power gamma minus 1 upon gamma. So, if we plug in the value of T1, that equal to 300 and P2 by P1 equal to 1.8 by 1 power gamma minus 1 upon gamma, that is 0.4 by 1.4. Take gamma equal to 1.4, and then we will be getting T2s equal to 354 Kelvin. Okay. So, if we plug in the value over here, then we will be getting T2, that equal to, if we erase this part, so this is T2, and from here we can write T2 equal to 354 minus 300. Isentropic efficiency of the compressor is given 75%, so 0.75 plus T1, that equal to 300. So, this is coming as 372 Kelvin. So, this is very important. So, if we go to the next slide, then we can calculate the power input needed for the compressor. So, power input to the compressor, that equal to P in m dot air into Cp air into T2 minus T1, actual compression, right. If we go to the previous slide, we can see that actual compression is from 1 to 2, right, and these two conditions are the manifold conditions that we have mentioned over here. So, that means the power input to the compressor for its operation should be this, and if we plug in the value, because already m dot air that we have calculated, right, actual we have already calculated 0.472 kg per second, that is the actual mass flow rate of air through the engine. So, then if we plug in the value, we will be getting 0.472, Cp air is taken as 1.005 kilojoule per kg Kelvin into this is 372 that we have calculated, and T1 is 300, and it is coming as 34.15 kilowatt. So, this is answer to the first part of the questions, and then we have to calculate second part of the question, that is we have to calculate if the exhaust gas temperature from the engine is 95 Kelvin. So, exhaust gas temperature is 950 Kelvin. If we go to the previous slide, so that exhaust gas temperature from the engine is 950 Kelvin, then we have to calculate pressure at the turbine inlet. Okay. So, what we can do, we can assume this is given, we can assume that there is loss of power, no loss of power as power developed by the turbine is transmitted, is given to the compressor. So, there is no loss of power. If we assume that, then if we consider the TS diagram for the turbine, then we can write. So, this is the power output or this is the power input needed for the compressor. We are assuming that the input power of the compressor or power given to the compressor is exactly output power of the turbine. If that is the case, then we can write m dot exhaust gases into Cp exhaust gas into T1 prime minus T2 prime actual. So, not isentropic. So, this is the isentropic expansion, this is the actual expansion in the turbine equal to 34.15. So, let me draw the HS diagram once again. So, this is what we could consider. So, this is 1 prime, this is 2 prime. So, we are just to avoid confusion we are giving 1. So, for example, the expansion is taking place from 1. So, this is P1 prime, this is P2 prime, this is 1 prime and this is the, so this is isentropic expansion while this is actual expansion. So, we are going to consider the actual one because frictional losses will be there. So, this is the expression. Now, from here we can calculate easily that the T1 prime minus T2 prime that would be equal to 34.15 divided by the exhaust m dot exhaust that mass flow rate of air. So, this is again assuming that this is 0.472 into Cp exhaust is 1.147. So, Cp exhaust gas it is given as 1.147, this is kilojoule per kg Kelvin. Okay. So, we are assuming that mass flow rate of exhaust gas. So, assuming that mass flow rate of the exhaust gas is equal to the mass flow rate of air. Certainly, during intake strokes mass of air will be inducted, then certain amount of fuel will be sprayed, but the amount of fuel is not very high. So, we are assuming that mass flow rate of air that is drawn in to the engine cylinder or inducted in the engine cylinder is equal to mass flow rate of exhaust gas. So, if that is the case, then we can calculate this is coming as 63.08 and that equal to T1 prime minus T2 prime, right. So, if we talk about isentropic efficiency, then from this we can calculate this from here T1 prime minus T2s prime this equal to T1 prime minus T2 prime divided by eta isentropic turbine, right. So, eta isentropic turbine equal to T1 prime minus T2 prime, that is actual expansion divided by isentropic expansion. So, from there we can calculate easily, here it is given T1 prime equal to 950 Kelvin, that is exhaust gas temperature, that is the inlet temperature of exhaust gas or exhaust gas temperature at the inlet of the turbine is 950 K, and so this is given, and then already we have calculated T1 minus T2 prime from this expression. We know the isentropic efficiency of the turbine, from there we can calculate this fellow. So, if we go to the next slide, we can easily calculate T1 prime minus T2s prime, that equal to T1 prime minus T2 prime divided by eta s turbine, and this equal to 63.08 divided by eta isentropic turbine, that equal to given 0.6 if I can recall correctly. So, this is I think 0.6. So, from there we can it is coming as 105.14. So, from there we can calculate T2s prime equal to T1 minus T1 prime minus 105.14, and it is coming as 844.85 Kelvin. So, this is the case. If we assume gamma exhaust gas equal to 1.33, then we can use isentropic relation, that is P exit turbine divided by P inlet turbine, that equal to T2s prime divided by T1 power 1.33 divided by 0.33, gamma minus 1, gamma by gamma minus 1. So, if we calculate the value and P in or inlet pressure to the turbine, is given. So, we have to calculate this, while exit pressure is ambient. So, P exit turbine equal to 1 atmospheric pressure, that is given, that turbine exhausts to atmosphere. So, if we calculate, we know this T2s, we know T1. So, then finally, if we calculate, we will get P in turbine equal to P exit turbine into T1 by T2s prime or T1 prime, that power 1.33 divided by 0.33, and it is coming as 1.58 atmospheric pressure. So, this is what is the final answer of this question, that is the inlet pressure that we had to calculate what is the pressure at the inlet of that turbine inlet. So, this is 1.58 atmospheric pressure. So, certainly that exhaust gases are fed into the turbine, and pressure of the exhaust gases is not equal to the atmospheric pressure, which you can see from this calculation as well, that the exhaust gas pressure is little higher than the atmospheric pressure. So, to summarize our today's discussion, we have talked about performance map of superchargers, which is nothing but the performance map of compressors. Thereafter, we have while we have discussed about this performance map, we have seen a few salient points. Thereafter, we have solved our numerical problem to illustrate the theoretical part that we have discussed in the context of supercharging. So, with this I stop here today, and we shall continue our discussion in the next class. Thank you.